Hello everybody, today we'll discuss deflection of beams. Before starting this chapter, we'll review the previous chapters that we completed earlier. First, for axially loaded member, we already know the stress sigma equals to P divided by A and delta equals to PL divided by AE. P is the axial load, L is the length of the member, A is the cross-sectional area, and E is modulus of elasticity. Then for torsional element, if you see this element which is subjected to a torque, the shear stress, we can calculate tau equals to P rho divided by J. And the torsional deformation, which is also known as angle of twist and represented by phi equals to TL divided by GJ. T is the applied torque, L is the length of the member, G is modulus of rigidity, and J is polar moment of inertia. Similarly, if we consider a member or beam which is subjected to bending, then we know how to calculate the stress. This is the stress, sigma equals to my divided by I, but we don't know how to calculate the deformation. In this class, we'll learn how to calculate this deformation. Consider the beam is a simply supported beam. That is the hinge and this is a roller support and subjected to a transverse loading. That means load is applied perpendicular to the axis of the beam. Due to this load, the beam will deform and this dotted line shows the deformed shape of the beam. This deformed shape of the beam is known as elastic curve. Our target in this chapter is to calculate this deformation y at any distance x. How to calculate this deformation y at any distance x we'll learn in this chapter. Many methods are available to calculate the deflection of beams. I have indicated here 5 methods: double integration method, area moment method, strain energy method, conjugate beam method, and method of superposition. Among these 5 methods, we'll learn the first 2 methods, double integration method and area moment method. These 2 methods we'll learn in this class. The content of this chapter is how to draw bending moment diagram by parts and how to draw deflection of beams by integration method. Now, what is bending moment diagram by parts? Bending moment diagram by parts means each load and reaction on the beam will produce a separate moment diagram. The resulting diagrams are said to be drawn by parts. If we combine all these individual diagrams together, then we'll get an equivalent bending moment diagram for the beam. Generally, 4 types of load come on the beam. These are the moment, the concentrated load, the uniformly distributed load, and the triangular load. We'll see for a cantilever beam how to draw the moment diagram for these 4 types of load. This is a cantilever beam. The fixed support is here. And if we apply a moment here, negative moment, why it is negative? Because it will create compression at the bottom fiber. Then how to draw the bending moment diagram for this? If you draw the bending moment diagram, you'll see it is minus m. The reaction moment here will be m also in this direction. And if you draw this moment diagram, it will be a horizontal line because this moment will remain constant throughout the beam. So this is the moment diagram. Second, if you consider the same beam but subjected to a point load, this point load is P, the span of the member is X, then what will be the moment diagram? The moment diagram will be a first degree curve, linear line, and the ordinate will be here maximum moment P multiplied by X. If we take the same beam and draw the bending moment diagram for uniformly distributed load, what will be the shape of the moment diagram? The moment diagram will be a second degree curve, and the maximum moment will be Wx squared divided by 2. If you consider the same beam, the beam is loaded by a triangular variation of load as shown in figure. This is W kilonewton per meter, and here it is 0. The bending moment diagram will be a third degree curve, and the maximum moment will be Wx squared divided by 6. If you can remember the shape and the ordinate of these 4 diagrams, that will be very much helpful in later stage when you will draw bending moment diagram by parts. Now we will consider 2 examples how to draw bending moment diagram by parts. The example presented here is 15.2 of your text. In this example, cantilever beam has 2 types of load. One is point load, another one is distributed load. You have to draw the bending moment diagram for these 2 loads separately. If you consider the point load only, the moment diagram will be, as you know, it will be a linear line or first degree curve, and the ordinate will be P multiplied by X. 36 multiplied by 4.5, it is minus 162 kilonewton meter. It is negative moment as the load is downward. If you want to find the ordinate here, you can easily find it is 36 multiplied by 1.5, that means minus 54 kilonewton meter. Now, if you want to draw the bending moment diagram for this uniform load, it will start from here and it will be a second degree curve. So it is a second degree curve. The ordinate here will be Wx squared divided by 2. W is 20, X is 3 square divided by 2 will give you minus 90 kilonewton per meter. So this complete your moment diagram by parts. If you want to draw the combined moment diagram or equivalent moment diagram for this beam, you have to add these ordinates. 0 plus 0 will come 0 here. Minus 54 plus 0 here will give you minus 54 at a distance 1.5 meter. Here it is minus 162 minus 90 will give you, if you add these two, it will be minus 252 kilonewton meter. Here it is straight line, so it will come straight line. Here it is straight and second degree curve, so it will be some form of curve. You have to add between this point and this point with some form of curve to get the combined bending moment diagram. Next, see the example 15.3. In this example, it is a simply supported beam. It has uniformly distributed load. You have to calculate the reaction of this beam. If you calculate the reaction of the beam, you can find it is 4 kip here, it is 8 kip here. What we'll do, we'll fix here, we'll make it cantilever. If we fix here, then 2 load will be on the beam. One is this reaction, another one is uniformly distributed load. For this reaction is like a point load. For this reaction, linear bending moment diagram will come like this, and it is 4 multiplied by 12, that is plus 48. Why it is plus? Because the load is upward. Then for this type of load, that means for this uniform load, the moment diagram you can draw in a separate figure, but you can draw it here also. It will start from here. It will be a second degree curve. This is 1.5 multiplied by 8 squared divided by 2 will give you minus 48 kip feet. To combine these two bending moment diagram, you can simply add to the ordinate. Here it is 0. It will come directly to 0. Here it is plus 16 and here it is 0. So total will be plus 16. Here it is plus 32 minus 12. Total will be plus 20. And it is plus 48. It is minus 48. Here it will be by 0. If you can directly come along this line, you will find a 0. At 12 feet distance, the bending moment will be 0. At 8 feet distance, the bending moment will be plus 20. And at 4 feet distance, the bending moment will be plus 16. Here it is a straight line. So it will be a straight line until this point. Then here straight line and curved line. So all through it will be curved line. It is 16 here, 16 here. It is 20 here. So you have to add these 2 points by this direction of curve. Similarly, from here, it is a curved line and it is a straight line. So it is some form of curved line. So you have to add these two. We are not very much interested with this combined bending moment diagram. Unless it is written on your question, you no need to draw this one. We are interested with bending moment diagram by parts.